Welcome to the video geometric series, and we are going to be adding the terms in a geometric sequence. So if we consider the sequence 2.5, 5, 10, 20, and 40, we could just go ahead and sum up these values and calculate that out to be 2.5 plus 5 plus 10 plus 20 plus 40. Punching that out in our calculator, that is equal to 77.5. But if we had a geometric series where it is either infinite or we have a lot of terms in our geometric sequence, we could spend a lot of time and most likely a lot of error calculating out the summation. And we'll come back to this problem, but this is the big puzzle that we have right now. And we'll be going over what we need to find the sum. But I would like to introduce to you the proof of how we come up with the summation formula for a geometric series. So in our previous lecture, we defined the explicit formula for a term of a geometric sequence, and that is a sub 1, our first value, times r to the n minus 1, where r is the common ratio and n is the term placement, and a sub 1 is the first term. So let's go and consider the summation of all of the terms generated by our rule. So the first term would be a sub 1 plus we have a sub 1 times r plus a sub 1 times r squared. And as we continue on, we'll go ahead and continue to a sub 1 times r to the n minus 2 plus a sub 1 times r to the n minus 1. And this specifically at the end is the explicit term of a sub n. That's what we have found in the last video. If we multiply what we just expanded out, our s of n, and if we multiply that by r, we can go ahead and multiply each of these terms that we are adding by another r, thereby expanding the exponents belonging to the r. So that's an r to the n minus 1 plus a sub 1 times r to the n. Let me go ahead and erase that little error that really should be an r there. Okay. If I were to subtract our first line of s sub n minus r times s sub n, you can see how these values, a lot of the terms in the middle of both of these expanded definitions, they end up canceling out. And when that happens, and what we are left with is a sub 1 and the last term of that multiple of s sub n is a sub 1 times r to the n. Okay, so let's go ahead and write that out. We have, let me change my pen color here. We have and are left with a sub 1 plus a sub 1 times r to the n. Now on the left hand side, let's go ahead and simplify this and extract s sub n, so we have 1 minus r remaining. And on the right hand side, let's take out a sub 1, which is 1 minus r to the n that is remaining. And if we were to simplify this and solve specifically for s sub n, we can rewrite this to generate a formula which gives us the summation of a geometric sequence in terms of the first value, a sub 1, our geometric common ratio r, and n. And so this is the proof of how we come up with our summation notation for a geometric series. For the remaining part of these videos, we are going to find the sum of finite, and this is arithmetic, and it shouldn't say arithmetic, it should say geometric. sequence. We also call this the nth partial sum. Most geometric sequences and series that we deal with will be infinite, so we are capping the summation at a value which makes it an nth partial sum. We will use S sub n, as we just notated above, to evaluate a summation. This is my favorite part. We are going to understand how series apply to salaries and annuities. And we are lastly going to find the sum of an infinite geometric series. So our first objective, we are going to find the sum of the finite geometric series, and we'll go ahead and write in our definition that we have just proved. But first, before we do that, I want you to recall the summation notation, or sigma, and how it relates to the series. So this is saying that we are going to take the summation of a series generated by this rule a sub 1 times r to I minus 1 all the way up to the nth term. So this is the summation. It tells you the boundaries, it tells you how far you can expand it out, and the definition behind that that belongs to the summation is the rule of the arithmetic sequence, and we are adding them all up. We can write this all out, but as we have just shown, that the sum of the first n terms are defined by taking that first value a sub 1 and multiplying it by 1 minus r to the n and dividing that by 1 minus r. So go ahead and write that in. Okay, now sliding back to page 5. We had started out in example 1 looking at this geometric series that we didn't yet solve for. And now we have the tools and the definitions that we need to solve for it. So taking a look at the relationship between each of the terms, 0.3 divided by 3, and then 0.03 divided by 0.3, we see that our common ratio is 0.1. We have a sub 1 equal to 3 and n equals to 20, because we are asked to find the first 20 terms. So if we were to expand this out and use the definition to find s sub n, we have 3 times 1 minus 0.01 to the 20th power all over 1 minus 0.1, and that equals to 3.33 repeating. So the summation of the first 20 terms of example 1 is 3.33 repeating. Let's continue on to example number 2 on page 6. So for example number 2, we are asked to find the summation notation of the listed sequence here of 3 plus 6 plus 12 plus 24, and the first 8 terms of the series. Oh, the sum of the first 8 terms of the series. So the first thing I'm going to do is I want to recognize the rule of this geometric series. I can see that the relationship between each of these terms gives the common ratio to be 2, and a sub 1 equals 3, and n equals 8. And so our rule, oops, let me go ahead and slide that over. Our rule is defined by a sub n equals 3 times r to the n minus 1. Now using sigma notation, the first thing that you want to start off with is the actual sigma symbol, and this goes from I equals 1 all the way up to 8. And so that is where we start, that is where we end, and we also have our rule that we need to insert into this notation. So I have 3 times r to the I minus 1. I is generally used, same with j and k. We can also use n, but I is often most likely used. We could go ahead and expand every single term and add it up, or we can use our defined S sub n formula, which states that we take that first value 3 and we multiply it by 1 minus the r value, which is 2, raised to the 8th power over 1 minus 2. And if I were to calculate this out, we end up with the sum of the first 8 terms of the series to be 765. Going down to example 3, we are also asked to find the summation notation and the sum of the series from 3 all the way up to 1,536. And the biggest question here that you may have asked is, what is our n? We have our common ratio to be 2. We know our first starting point of 3, but we don't have our n value. Well, we can actually use logarithms to solve for n. So if our a sub n, our nth term, that when we're trying to find m, is equal to 1,536, and we know our general rule of 3 times 2 to the n minus 1, you can see how we can solve for n by using logs. And I choose to use the natural log. If I take the natural log of both sides, let me go ahead and first divide both sides by 3 to get rid of that. I forgot about my 3 there. So if I divide 3 by both sides, I end up with 512 equals to 2 to the n minus 1. I'm going to swing this up here. I can go ahead and take the natural log of both sides. So the natural log of 512 divided by the natural log of 2 equals to n minus 1. And this on the left-hand side calculates out to 9 equals n minus 1. And so 10 is n. We can now use our sigma and summation notation to calculate the sum based on the information that we have. So erasing this through, when you have a little bit of more margin space than what I have on my video here. But go ahead and start writing the summation notation, and get my correct pen color. I have the sigma, the summation of I equals 1 all the way up to 10 of my rule, and we've already figured that out, which is 3 times 2 to the n minus 1. And using our S sub n formula, this generates to 88,572. So we have a got it question number 4 for you to solve, and we'll continue on to page 7. Okay, here we are asking objective 2. We're going to use S sub n to evaluate a summation. So let me go ahead and color this through. I think we lost some colored values there. Okay. We are given a summation already, and all we need to do is go ahead and use our S sub n notation. In this case, our n is 10. So we're going to find the sum of the first 10 terms of our listed geometric series. And if I use the formula using the first a sub n equals 5, or a sub 1 equals 5, and multiply that by 1 minus negative 2 to the 10th power, all over 1 minus negative 2, we can easily find our value and solution. And calculating that out, we end up with negative 1705. Go ahead and double check my work and see if I did that correctly. And pause the video. Actually, this is the end of video A. Go ahead and solve got it question example number 6 and number 7, and join me for the next geometric series video B.